Hey everyone, we're back with another banger today. We'll be doing February-March 2023, 9702, paper 42. So the paper isn't out yet officially, so I don't have access to the threshold yet. So without further ado, let's begin. Starting with question number 1. Define gravitational potential. Okay, so it is the work done per unit mass to move the unit mass from infinity to a point inside the field, alright? So it is the work done per unit mass and the work is done moving the mass from infinity to the point inside the field. So in one line, you could simply state that it is the work done moving unit mass from infinity to the point inside the field. That would work. Artemis is a spherical planet that may be assumed to be isolated in space. The variation with distance x from the center of Artemis of the gravitational potential is shown. Gravitational potential is a negative value. You guys already know that. The radius of Artemis is 4,800 kilometers. Determine the value of phi on the surface of Artemis. Seems as if they've changed the symbol for phi starting from this variant. 4,800 kilometers. Okay. So what is 4,800 km? It's basically 4800 times 10 to the power 3 or 4800000 meters, which is 4.8 1, 2, 3, 4, 5, 6 times 10 to the power 6 meters or 0.48, right? 0.48 into 10 to the power 7 meters. Okay, so you had to find out 0.48 over here. 0.1, 0.2, 0.3, 0.4, 0.5. This is 0.5. So 0.48, this is 0.45, right? So 0.48 should be a bit above 0.45, a bit later than 0.45. So essentially somewhere over here, yeah? Somewhere over here. Just behind 0.5. So if you do match the value, you are going to get this particular value. This is the value of the surface. Oh, we could just match it. This was the value of the surface. You could just match it with this, essentially. But if you do that, the problem is, wait, it's over here, yeah? So this is 3.6, 3.7, 3.8, 3.9. So my point over here is between 3.5 and 3.6, so it's at 3.55 into 10 power 7, okay? But it's going to be a negative value. The minus sign must be included. Minus 3.55 into 10 to the power 7 joules per kg. Show that the mass of Artemis is this. So guys, the formula for phi is minus gm by r. So we know the value of phi is minus 3.55 into 10 power 7 is equal to minus g. The value of g is 6.67 into 10 to the power minus 11 times the mass divided by the radius, which is 4,800 kilometers or 4,800 into 10 to the power 3 meters. You can get rid of the sign. So mass is basically equal to 3.55 into 10 power 7 times 4800 into 10 to the power 3 by 6.67 into 10 to the power minus 11. I got the value for 6g from the data booklet. I just have it memorized. You can see it from use it from the data booklet. So 3.55 into 10 to the power 7 times 4800 times 10 to the power 3 divided by 6.67 into 10 to the power minus 11. We're getting a value of 2.55 into 10 power 24. Okay, so why did I choose a 3SF value? They told us to show it. Also, all our data, they're all given to 3SF, right? Calculate the field strength on the surface of Artemis. Okay, so what's the formula of field strength? Field strength is equal to Gm by R square. So let's do this. G is equal to 6.67 to 10 to the power minus 11 times 2.55 times 10 to the power 24 divided by R square, which is 4800 times 10 to the power 3 whole square. Since it's a show question, I'm going to carry forward the answer. I'm not going to use my calculator value. I'm using 2.55 into 10 to the power 24 times 6.67 into 10 to the power minus 11 divided by 4800 times 10 to the power 3 whole square. We get a value of 7.38 into 10 to the power, just 7.38, no power. Correct to 3 significant figures. So all our data here, this is given to 4SF, this is given to 3SF the mass, this is also given to 3SF. So you should be writing a 3SF answer. So in the mark scheme they wrote correct to at least 2SF. So you could either write 7.4 or 7.38, both work. So this is one route. What's the other route? You could also opt for this. Like, you guys know that the difference between phi and g is simply 1r. So there's a bridging formula between them. Basically, you could say that g is equal to phi by r. This is the relationship between them. So g is equal to phi, which is minus 3.55 times 10 to the power 7, divided by 4800 times 10 to the power 3. Let's do this. We get a value of 7.395, or this is basically 7.40. Okay. Anything works. We got 7.40 rather than 7.38 because the accurate value was used rather than the rounded up value of 2.55. If you use the correct value from the raw value from the calculator, you would be getting 7.40. Anything works, honestly, since they wrote a minimum of 2 significant figures. Okay. Okay, for part 4, we have a satellite. The satellite is in an orbit at a fixed position above a point on the surface of Artemis. The satellite is located above the equator of Artemis at a height above the surface where the gravitational potential is minus 0.65 times 10 to the power 7. Calculate the period in hours of rotation of Artemis. Okay, so we know that the gravitational force provides the centripetal force. So mv squared by r is equal to gmm by r square. And we know that v is equal to omega r, or v is equal to 2 pi by tr. So we can actually write this as m omega square r is equal to gmm by r square. We can get rid of the m over here. So 2 pi by t whole square, what do we end up with? 4 pi square by t square times r is equal to gm by r square, or 4 pi square by t square times r cube is equal to gm. Now if you make t square the subject, you end up with t square is equal to 4 pi square r cube by gm. So t square is equal to 4 pi square times, now we have to find out the radius r. How do we do that? Our satellite is a geostationary satellite, by the way, because it's at a fixed position and it's on the equatorial orbit. So we have to match it with the graph. This value minus 0.65 into 10 power 7. So where is that? This is minus 0.6, so minus 0.65 is over here. If you match it on the graph, if you see closely, Where does it match? It actually passes this point and matches somewhere over here. Somewhere over here. So guys, this is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. So it's above 2.6 but less than 2.65. It is probably at around 6.2 or 6.3. The only way to confirm is doing it mathematically. For example, we can do this. We know that the value of gm is a constant, right? We know that phi is equal to minus gm by r. Can we not write this, that minus 0.65 times 10 to the power 7 is equal to minus 6.67 into 10 to the power 11 minus 11 times the mass 2.55 times 10 to the power 24 divided by r. So if you solve this, let's do it. 6.67 into 10 to the power minus 11 times 2.55 times 10 to the power 24 by 0.65 into 10 to the power 7. We're getting a value of this. R is equal to 2.617 times 10 to the power 1, 2, 3, 4, 5, 6, 7, which is rounded off to R is equal to 2.62 times 10 to the power 7. So yeah, it's 2.62 over here, 2.62 into 10 to the power 7. So for some reason in the mark scheme, they actually wrote 2.68, 26,800 kilometers. I've been trying to figure out why for some time, but I really don't know why, honestly. It's probably a mistake in the mark scheme since it's pre-standardized. It might be fixed in the main mark scheme when it comes out later in May. So for now, let's just go with this value, okay? If any updates do come up later, I'm gonna update it in the comment section or the description below. Alright guys? So t square is equal to 4 pi square times r cube 2.62 times 10 to the power 7 cube by gm 6.67 times 10 to the power minus 11 times 2.55 times 10 to the power 24. Let's do this. 4 pi square times 2.62 times 10 to the power 7 cube by 6.67 into 10 to the power minus 11 times 2.55 into 10 to the power 24. So we get this value t square is equal to 4.17 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the power 9. After you root over the answer, you actually get t is equal to 6.46 times 10 to the power 4 seconds. Now, to convert this to hours, you have to divide it by 3600 by 3600. So this gives me a value of t is equal to 17.9. So it's going to be rounded off to 18 hours since I have 2SF data in the question. So in the mark scheme, they actually wrote 19 hours because they said that it was supposed to be 18.6. However, I stated that the value of R might be wrong. The value of R might be wrong. So according to my value of R, it's actually 18 hours, I mean, not 19. Okay, so more on this later if anything does come out. State one similarity and one difference between gravitational potential due to a point mass and electric potential due to a point charge. Okay, so from similarity, you actually have three options. You can state that both of them follow the inverse square law, which means that the potential, not inverse square, both phi and electric potential V, they're inversely proportional to R. Okay, so both of them are inversely proportional to distance from a certain point. And the other one, points of equal potential lie on the concentric sphere. This means that there's an equipotential surface. So if you have a concentric sphere, this point, and this point as well, they all have the same potential. Okay, so the other point is points of equal potential lie on concentric spheres. Fine. And what is your third option? You can also opt for there is zero potential at infinity. Zero potential at infinite distance. What is the difference though? Gravitational potential, remember, it is always negative. Okay, so but electric potential can be positive. Gravitational potential is always negative. Or you could state that it's the same point, although electric potential can be positive or negative. Is that fine? There you go. Moving on to question 2. State what is meant by an ideal gas. So it follows the ideal gas laws, right? So it is a gas for which PV is actually proportional to the thermodynamic temperature, where we have to specify T is the thermodynamic temperature or the temperature in Kelvin. Okay, that's fine. That's allowed. A fixed amount of helium gas is sealed in a container. The helium gas has a pressure of this pascals, 1.1 into 10 power 5, and a volume of 540 cm cube, and temperature of 27 degrees Celsius. We need to convert these. Show that the helium behaves as an ideal gas. Okay. So, guys, you know that PV is equal to nRT, or PV by T is actually a constant nR. So, let's equate them. On the left hand side, we have 1.10 times 10 to the power 5 times 540 divided by the thermodynamic temperature, 27 plus 273. And on the right side, we actually have 6.70 times 10 to the power 6 times 30.0 divided by 742 plus 273. I did not bother converting cm cube to meter cube because it would cancel out on both sides, yeah? Next. So 1.1 into 10 to the power 5 times 540 by 27 plus 273. That gives you a value of 198K. And this one on the right hand side, 6.7 times 10 to the power 6 times 30 divided by 742 plus 273 gives you a value of 198K as well, 198029. So since the values are same, so it's an ideal gas. Okay. Now, the first law of thermodynamics may be expressed as this. Using the first law of thermodynamics to explain why the temperature of the helium gas increases. Use the first law. So guys, an ideal gas does not have any potential energy because of the absence of intermolecular force of attraction. So you guys know that the sum of random distribution of K and P is equal to the internal energy. However, there is no potential energy. So all the increase in Ke is converted to the increase in internal energy. Now, what happened in the final state? The temperature increased, right? So obviously heat was supplied from outside. And if you increase, the volume has decreased, right? So work is done on the gas. So it's stated like it's the volume of the container is rapidly decreased. Okay, so you can't talk about thermal energy being supplied to the gas because this is the key point. The volume of the container is rapidly decreased. So you guys know that work done on a gas is written as P del V. At constant pressure, if you decrease volume, work is done on the gas, right? So work is done on the gas as its volume decreases rapidly. So W is positive. Nothing is said about Q. So since W is positive, del U also has to be positive, right? So internal energy U, internal energy increases. Okay, internal energy increases, so temperature also increases. Pretty straightforward. Okay, moving on. The average translation energy of one molecule of an ideal gas is given by this equation. Calculate the change in total energy of the molecules of the helium gas. Okay, so to do this, I need the total number of molecules of the gas by using the equation PV is equal to NKT. So N is actually equal to, you can use either end. I'll just opt for the one on the left hand side. So 1.1 into 10 power 5. Volume is 540, right? 540 cm cube. So I gotta convert that to meter cube into 10 to the power minus 6 divided by kT. K is 1.38 into 10 to the power minus 23. And temperature, what was the temperature? It's 27 plus 273, which is 300 Kelvin. So let's see what we get. 1.1 times 10 to the power 5 into 540 into 10 to the power minus 6 divided by 1.38 times 10 to the power minus 23 times 300. This gives you a value of 1.435 times 10 to the power 22. So what is the change in kinetic energy? If you think about the whole thing, 1.38 into 10 to the power minus 23 times the temperature 300 Kelvin times the number of particles, which is 1.435 into 10 to the power 22. Okay, times 300 times 1.5 times 1.38 times 10 to the power minus 23. This gives you a value of 891 by 89.1. So since our data is given to a minimum of, 2SF over here, and hear me out, there's another step over here. Calculate the change in total kinetic energy. What I found out over here was actually the kinetic energy of the initial state. Do you guys understand? You can find out the number of molecules using any of these states, either the initial one or the final one. You will always get this answer. But now the tricky part is we need to find the change in total kinetic energy. So I found out the initial kinetic energy. Now I need to find out the final one, right? So let's do that. This is the initial Ke. What about the final one? Almost the same thing. 3 by 2 into 1.38 into 10 to the power minus 23 times, what's the final temp over here? 742 plus 273, 1015. Times n, 1.435 times 10 to the power 22. Okay, 1.435 times 10 to the power 22 times 1015 times 1.38 times 10 to the power minus 23 times 1.5. This gives you a value of 301.5. So if you find out the change in total kinetic energy, it's going to be 301.5 minus 89.1. This gives you a value of 212 to 3SF. So that is your final answer, 212 joules. In the mark scheme, they went for an alternate approach. I'll also show you that if you guys want. Let me push this away over here. So the other way is doing it directly. What does that mean? Basically, you could write del Ek directly like this. Del Ek is equal to 3 by 2 K del T times N. So it's 3 by 2 times 1.38 times 10 to the power minus 23 times del T. You can just deal with the, like here you don't need to convert it to Kelvin because regardless, like here you are adding 273, here you're adding 273. So if you subtract these two values, these values we can get rid of them, right? So it's basically 742 minus 27, 742 minus 27 times the value of n, which is 1.435 times 10 to the power 22. Let's do this. 742 minus 27 times 1.435 into 10 to the power 22 times 1.5 times 1.38 into 10 to the power minus 23. Yeah, this gives me a value of 212. Okay, that's that. The mass of nitrogen gas in another container is 24 grams at a temperature of 27 degrees Celsius. The gas is cooled to its boiling point of minus 196. Assume that all the gas condenses to a liquid. For this change, the specific heat capacity of nitrogen is 1.04. The specific rate of vaporization of nitrogen is this. Determine the thermal energy removed from the nitrogen gas. Okay, so nitrogen gas was initially at 27 degrees Celsius. Wait, let me bring it over here, 27 degrees Celsius. So it was cooled to 0 degrees. It passed 0 degrees actually. The gas cooled to its boiling point, minus 196. So it goes down by a lot, by a large margin. Then I have to draw 27 here. Wait. Basically kind of like this. And then, all of it basically condenses to a liquid. So determine the thermal energy removed from the nitrogen gas as it turns into a liquid. Then it will cool down further, maybe, I don't know, but essentially we have to find out the total energy removed. Okay, so there are two phases. One is for mc del theta, the other is for ml. Okay, so let's find out the thermal energy removed. So E is equal to mc del theta plus ml, right? So what is the mc del theta over here? We have to convert it to kg, by the way. So 24.0 times 10 to the power minus 3 times C, which is 1.04 kilojoules, right? So it's fine. Times the temperature change. It's actually 196 plus 27. So this is one portion. This is the first part. What about the second part? 24.0 times 10 to the power minus 3 times ml, which is 199. So 24 into 10 to the power minus 3 times 1.04 times 196 plus 27. That is 5.56608 plus 24 into 10 to the power minus 3 times 199, which gives you a value of 4.776. So this gives you a total value of 10.34208. So our data is given to three significant figures here, right? All of it is given to 3SF. Like here 27 is given to 2SF, but you're technically using the 3SF value after you add the Kelvin 273, right? As a result, you have to give the answer to 3SF. So we end up with 10.3 kilojoules. That is our answer. Okay. There you go. So we had this section where we cooled down, and we had this section where we were, condensing to form the liquid again. That's that. Question number 3. An object is suspended from a vertical spring as shown. The object is displaced vertically and then released so that it oscillates, undergoing simple harmonic motion. The kinetic energy, the potential energy, and total energy are represented by PQR. So P is the total energy, it never changes. Okay, so P is the total energy. So about potential energy, you will have maximum potential energy at the ends, okay? And you will have maximum Ke at the equilibrium position, and you will be stationary for a bit at, the maximum position. So at that point, K will be 0. So R is clearly the kinetic energy. Okay, you need to remember this graph. This is very important. So Q has to be the potential energy. Now the object has a mass of 130. Determine the period of oscillations. Fine. let's do this. So we can use the help of energy. We know that the total energy is actually 6.1234. It's 6.4 millijoules. So energy, the formula for energy is half m omega square x naught square. Yeah. So 6.4 times 10 to the power minus 3 millijoules, right, is equal to half times 130 times 10 to the power minus 3 times omega. Omega is essentially 2 pi by t whole square. And what is x naught over here? We can check that from the graph. Your maximum displacement is 1.2, 1.4. Looks like it's 1.5. Okay, so that's 1.5 centimeters. That's 1.5 into 10 to the power minus 2. So let's solve this. They actually kept omega square as omega square initially. So let's do this. 6.4 times 10 to the power minus 3 into 2 divided by 0.130 divided by 1.5 into 10 to the power minus 2. This gives you a value of omega square is actually equal to, wait, there's a square over here, divided by 1.5 into 10 to the power minus 2. Yeah. So omega square is actually equal to 438 to 3SF. So omega is equal to root over answer, which gives you 20.9. So you guys know that omega is equal to 2 pi by t. So 2 pi by t is equal to 20.9. So t is actually equal to 2 pi divided by 20.9. So that gives you a value of 0.300 or 0.30 essentially, 30 seconds. There you go. They also accept 0.300 here. State the cause of damping. So what is damping? Damping is loss of energy of oscillations due to resistive force. Okay. So what is the resistive force? Mainly a force that is in the opposite direction to motion. Okay. If nothing else is specified, you just have to say that it is due to a force in the opposite direction to motion. If nothing else is specified. If you are given a specific scenario, you have to talk about it in details. A light card is attached to the object. The object is displaced with the same initial amplitude and then released. During each complete oscillation, the total energy of the system decreases by 8% of the total energy at the start of that oscillation. Determine the decrease in total energy of the system by the end of the first 6 complete oscillations. So every time, this is basically a geometric sequence. Every time you lose 8% of your total one. So if you lose 8%, how much are you left with? 92%. So essentially, we had, 6.4 millijoules. Now every time we are going to lose 8%. During each complete oscillation, the total energy of the system decreases by 8%. So we are left with 92%. Okay. So after each oscillation, you are left with 92% of your original one. And then this thing just repeats 5 more times. Do you guys get what's happening? So to put it simply, if you want to write this more simply, you can just opt for 0.92 to the power 6, like a geometric sequence. We are looking for the 7th term in the series. This is actually equal to 0.606. So we become 0.606 of the initial value. So we can write that the final energy is actually 6.4 millijoule times 0.606, which ends up being 0.92 to the power 6 into 6.4. This gives you a value of 3.88 millijoule. This is your final energy. So what is the energy lost exactly? It's the total energy, the initial energy minus the loss. Sorry, energy, initial minus final. 6.4 minus answer gives you a value of 2.5 millijoules. That's how you do this math. Interesting. I haven't seen this before. This is the first time I'm seeing this sum. State with the reason the type of damping. So honestly, 8% is very small, right? So every time we're losing a bit of energy, and it's not increasing every time. It's gradually decreasing. As a result, we're going to say that it's light damping. It is light damping because the amplitude of oscillations gradually decreases. Because the amplitude of oscillations gradually decreases. This is one way of saying it. What is the other approach? You could say that light damping because the system still oscillates. Okay, light damping because the system still oscillates. There you go. Moving on to question number 4. How many do we have in this paper in total? We have 12 or 13 maybe. Oh, we have 10 questions only. Interesting. So let's start question 4. State Coulomb's law. So Coulomb's law states that the electric force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation, right? So it states that the electric force between point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation. Great. A charge sphere X is supported on an insulating stand. Okay. A second charge sphere is suspended by an insulating thread, so that sphere Y is in equilibrium at the position shown in figure 4.1. So the charge on sphere X is 96 nanocoulomb and the charge on sphere Y is 64 nanocoulomb. Assume that the spheres behave as point charges. So sphere Y is in equilibrium, alright? It's held still. The length of the thread is 1.2 meters and the center of the sphere X and Y are separated horizontally by a distance of 0.8. Draw and label the forces acting on sphere Y. So clearly there's a thread, so a tension is acting. And then this is the direction of tension. Then we have a weight which is acting vertically downwards. What else do we have? We have an electric force. So how will the electric force act? Basically, since they are horizontally spaced, it will act along this line. Both of them are positive, so it will actually feel repulsion. Okay, so let me make this straight. Wait. So this is the electric force. There you go. See if it makes sense for you guys. Okay guys, these are the axes. We're going to show this. There you go. Okay. Determine the mass of sphere Y. Interesting. So the net force is going to be 0. You can actually find out the angle. Okay, you can find the angle to the vertical. Basically, check this. If I draw a picture like this is 90 degrees. I can actually find out this theta. How? I know that this length over here, this one, is 0.080 and this is 1.2. So sine theta is equal to opposite by hypotenuse, right? So sine theta is equal to opposite 0.080 by hypotenuse 1.2. Let's find that out. 0.08 by 1.2 sine inverse answer. That gives me a value of theta is equal to 3.823 degrees. Interesting. So guys, you know that the weight is acting like this, vertically downwards, and the electric force is acting this way, horizontally to the right. Electric force EF. And what about this? Um, it basically has one component upwards and another component that is directed towards the right. And since this is theta, this angle over here is also theta at 3.823. Okay, I'm going to store the answer. So now, how do we do this? Essentially, the vertical component of tension will balance weight. Okay, the vertical component of tension will balance weight. That's literally it. Because the electric force is actually acting horizontally. They are in line, right? Yeah, they are horizontally in line. Or you could do this. The electric force is equal to T sine theta. That also works. For some reason, they actually used tan theta. But it doesn't have to be that way. Like, since it's in equilibrium, what they did was they actually found this out. Like, they found out the resultant of these two forces and then, equated with tension. Why don't I try doing this? According to my diagram over here, T cos theta is equal to weight. But sadly, I don't have the value of tension, right? Which is why I can't apply that method. Which is why I need to find out the value of Fe first. Okay, that's what's required. So let's find out Fe. So Fe is equal to 1 by 4 pi epsilon naught times q by r square. So Fe is equal to 1 by 4 pi epsilon naught is actually 8.99 into 10 power 9. They actually use the exact value of epsilon. 1 by 4 pi times 8.85 times 10 to the power minus 12. And what is the distance between them? It's 0.080 meters, right? So 0.08 whole square. And in the numerator, we are going to have 64 nanocoulomb and 96 nanocoulomb. Okay. 64 into 10 power minus 9 and 96 into 10 to the power minus 10. So what do we end up with? 6.64 into 10 to the power minus 9 times 96 into 10 to the power minus 9 divided by 4 pi times 8.85 into 10 to the power minus 11 times 0.08 square. So you get this value. You get 8.63 times 10 to the power minus 4 newtons. This is your value for electric force, right? Now, what's our next goal? So we have this force F. I know that this value is going to be balancing out, the horizontal component of tension. Okay, that's one way of doing it. I'll show you another way, the one they used in the mark scheme. I'll show you that. That also works. It's up to you guys. So check this. Now I am going to do this. I'm going to find out the value of tension. How exactly? So I can write that T sine theta is equal to this value, 8.63 times 10 to the power minus 4. So T is actually equal to 8.63 times 10 to the power minus 4 divided by, 0.08 by 1.2. Let's do this. 0.08 by 1.2. Okay, so I'm getting a value of T is equal to 0.0129 newtons. Now what's the final step? We know that weight will be balanced out by the vertical component of tension, T cos theta. So I can write this, that T cos theta is equal to weight, or T cos theta is equal to mg, or m is equal to T cos theta by 9.81, which is, m is actually equal to 0.0129 times cos 3.823 divided by 9.81. Let's do this. So we get this value, 1.32 into 10 to the power minus 3. So since my data is given to 2SF, I'm going to opt for the 2SF answer, which is 1.3 into 10 to the power minus 3 kg, or 0.013. Is that fine? So let me show you what they did in the mark scheme. Like, my method is completely alright. You can follow this if you guys want. It's okay. So what they did was, they wrote this. Weight is equal to electric force divided by 10 3.82. So weight is equal to 8.63 times 10 to the power minus 3 divided by 10 3.82. Then they divided by g. So how does this work? So essentially, what do we have here? This is a vector diagram, right? And we know that this angle over here, is theta. And this is the resultant force. This resultant force R is the combined resultant force of Fe and W, which as a whole balances out this T. So R is the resultant force of Fe and weight. So check this out. We know that this value over here is Fe, this one. So think about this. You have theta over here, you have the opposite length, and you also have the vertical length. So can we not apply this, that tan theta is equal to opposite, which is Fe divided by weight? So weight is equal to Fe divided by tan 3.823, which will give you the same answer as 0.129. And then you know that mg is equal to 0.129. So m is equal to 0.129 divided by 9.81, which is 0.013. So that's how they did it. Now you can use my method if you guys want, but since they did this in the mark scheme, I would recommend doing it. Okay, they just use the resultant value R of W and Fe to balance out tension, and we know the angle already, right? So that just helps us exploit this that much more. Okay, so I'm going to move this away on the right hand side, and let me bring that method over here. Here you go. Okay, next, calculate the total electric potential energy stored between x and y. So what's the electric potential energy? What's the formula? EP is equal to Q1 times Q2, 1 by 4 pi epsilon into QQ by R, divided by 4 pi epsilon naught into R. So EP is equal to 64 times 10 to the power minus 9 times 96 times 10 to the power minus 9 divided by 4 pi into 8.85 into 10 to the power minus 11, sorry, minus 12 times 0.08. So let's do this. You could just divide Fe by R, that would also be okay. 64 into 10 to the power minus 9 to 96 into 10 to the power minus 9 by 4 pi times 8.85 into 10 to the power minus 12 times 0.08, which gives you a value of 6.9 into 10 to the power minus 4. That's good. An electron enters the region between two parallel plates P and Q that are separated by a distance of 18 millimeters as shown in figure 4.3. So state the direction of the electric force on the electron between the plates. This is the positive plate because the negative plate is downwards because it's earthed at 0 volts. So the electron will clearly feel a force vertically upwards. Okay, which is accepted in the mark scheme, but honestly they wrote towards the top of the page. Or you could write towards plate P, or just upwards is fine. Determine the magnitude of the force acting on the electron due to the electric field. So what's the electric field strength? We can find that out using this formula, E equals to V by D, which is 250 divided by 18 into 10 to the power minus 3. Next, we know that F is equal to EQ. So F is basically equal to, 250 by 18 into 10 to the power minus 3 multiplied by 1.60 into 10 to the power minus 19. So 1.6 into 10 to the power minus 19 times 250 divided by 18 into 10 to the power minus 3. This gives you a value of 2.22 into 10 to the power minus 15. So our data is given to 2SF, so I'm going to opt for 2.2 times 10 to the power minus 15 newtons. Explain why the electron does not follow a circular path. Okay, so this is a great question. It will mainly be like a projectile. Okay, our electron already had a horizontal component of velocity towards the right, which is constant, but now it's going to feel a force which is vertical upwards. So one component of its velocity will change while the other remains constant. So what will it be like? It will technically be like a projectile, parabolic. Remember in AS, the horizontal velocity remained constant while the vertical one changed, which is why a circular path is not possible. And for circular motion, remember the requirement is the force needs to be perpendicular to your velocity all the time. But that is not always the case. Initially it is, okay, but after you enter the plate, then the force acts vertically upwards like this, it is not perpendicular to the velocity anymore. Initially it was, right? But later on, if it had to be perpendicular, it had to be like this, but later on it is no longer perpendicular to the velocity. Could I clarify? So here the answer should be, the force is not always perpendicular to the velocity. The force is not always perpendicular to the velocity. This is one statement you could write, or you could say that the force is always in the same direction. The force is always in the same direction. This is the first time I've seen this question as well. Remember this theory. Towards plate P. Interesting. This is the marking point then. They basically refer to centripetal force, where the force has to be towards the center. Yeah? Anyway, moving on to question number 5. We have a capacitor. So, a capacitor, a battery, a capacitor, a battery of electromotive force, EMF 12 volts, a resistor R, and a two-way switch are connected in the circuit as shown in figure 5.1. The switch is initially in position S. Okay, so the capacitor is charging up. When the capacitor is fully charged, the switch is moved to position T so that the capacitor discharges. At time T after the switch is moved, the charge on the capacitor is Q. Okay. Show that the capacitance of the capacitor is 1.5 microfarad. Let's do this. So we can use this point. This is basically a 2.9 microcoulomb, right? So ln Q is equal to 2.9. So Q is actually equal to e to the power 2.9 microcoulomb. How much is that? E to the power 2.9. So Q is actually equal to 18.2 microcoulombs. What's next? You know that C is equal to Q by V. C is equal to Q by V. We need to find out the capacitance. So I'm considering the initial charge. You guys know why, right? Because I know that the initial voltage of the capacitor is 12. I want to exploit that fact. So C is equal to 18.2 times 10 to the power minus 6 divided by 12 volts. So answer, wait, calculate answer into 10 power minus 6 divided by 12. This gives you a value of C is equal to 1.5 into 10 power minus 6 farad, or C equals to 1.5 microfarad. This is a show question, right? So we should carry forward this answer over here. Determine the resistance of R. Okay, so here we need to use the formula for discharging a capacitor. So remember, guys, the formula for Q. The formula for Q is equal to Q naught e to the power minus t by RC. So if you use ln, what would you end up with? Ln Q is equal to ln Q naught plus ln e to the power minus t by RC. So you actually end up with ln Q is equal to ln Q naught minus t by RC. So if you rearrange it, you actually end up with ln Q is equal to, t is on the x-axis, right? Minus 1 by RC. T is on the x-axis plus ln Q naught. This is your expression. This is the graph if you have a linear relationship, okay? And if you had a nonlinear relationship, it would simply be like this. So the gradient of this graph happens to be minus 1 by RC. So let's find out the gradient of the graph. You can take 2 points at random. So one of them being 0, 2.9. The other being, you can take this point, I'm assuming. So this is a 5.4, 1.6. 5.4, 1.6. It doesn't match. It doesn't match exactly because we shouldn't be taking the ends. Why don't we try another point over here? This seems like it passes through the midpoint. This seems like it passes through this, or you could be taking this. This seems like it's passing through the midpoint. Okay, let's try this point over here. So this is 3 at 2.15. 3 at 2.15. So 2.15 minus 2.9 by 3 minus 0. Yeah, that gives you a value of minus 0.25. That's the gradient. I could also try other points like this one over here. 3.62. Let's try that. 3.62. So 2.9 minus 2 divided by 0 minus 3. That gives you a value of this is 3.6, right? Sorry. 2 minus 2.9 divided by 3.6 minus 0. That gives you a value of 0 minus 0.25 as well. So multiple points work. It's just best that if you don't take this. Let's try this one last. 4 and 1.9. 4 and 1.9. So that's 2.9 minus 1.9 divided by 0 minus 4. That also gives you a value of minus 0.25. So any point works, okay? Just find out the gradient. So the gradient happens to be minus 0.25. And by writing this equation over here on the right, you could also state that the gradient is actually equal to minus 1 by RC. Okay, so minus 1 by RC is equal to minus 0.25. So you can get rid of the minus sign on both sides. So R is actually equal to 1 divided by C times 0.25. So R is equal to 1 divided by 1.5 into 10 to the power minus 6 times 0.25. So let's find this out. 1.5 1.5 times 10 to the power minus 6 times 0.25. That gives you a value of R is equal to 2.67 into 10 to the power plus 6. So recently I've been seeing a trend. They don't really carry forward the show answer anymore. Do you guys understand? They've been carrying forward the true calculated answer all the time. So because if I do this, I'm getting a value of 2.67. Okay, but it should be 2.64. So I'm going to try using the accurate answer. 18.2 times 10 to the power minus 6 divided by 12. It's 1.51, 1.51667. Now if I use this again, 1 divided by answer into 0.25. Yeah, I'm getting the value of R is equal to 2.64, which is rounded off to R is equal to 2.6. 2.64 into 10 power 6, so 2.6 into 10 power 6 ohms, corrected two significant figures. So this is an issue that I've been noticing from October, November 2022. They don't carry forward the show answer anymore. They are using the true calculated answer now. So food for thought. I guess we should go with this method since this is the most recent question paper. Let's move on to the next one. Calculate the energy stored in the capacitor at a time t0. So what's the formula for energy? So energy is equal to half CV square. So we can just opt for half into the value for C. You could also use half QV, that's fine. But we got to use the accurate value for C, which is 18.2 times 10 to the power minus 6 divided by 12, which is 1.5167 into 10 to the power minus 6 times 12 square, right? That's our initial voltage, 12. Okay, half CV squared. This into 12 square into 0.5 gives you an answer of 1.092 times 10 to the power minus 4 joules. So to 2SF, it is 1.1 into 10 to the power minus 4. Okay, that's great. If you used 1.5, it would match here as well. No biggie. But there was this one sum in ON22 where it didn't match, and there's this sum again. It's a miniature mistake. Just one mark will be lost. A second identical resistor is now connected in parallel with R. Okay, so now we have another resistor which is connected in parallel with R. The switch is initially in position S. When the capacitor is fully charged, the switch is moved to position T so that the capacitor discharges. At time T, after the switch is moved, the charge on the capacitor is Q. On figure 5.2, sketch a new line to show the variation of ln against T. Okay, so guys, hear me out. We know that ln Q is equal to minus 1 by RC times T plus ln Q naught. So here's the thing. 1 by RC is the gradient, right? Minus 1 by RC is the gradient. When this R represents the total resistance in the circuit and C is total capacitance. Total capacitance does not change because you bring about no change to the capacitor. But what happens to total resistance? Since you add another resistance to parallel, you know that an identical resistor, the resistor is actually going to, the total resistance is going to be halved. So since the resistance halves, what happens? Now, this was the initial gradient, this was the old gradient. Now the new gradient becomes minus 1 divided by R by 2 into C, which is minus 2 by RC. So the gradient actually becomes double of the initial value. Okay, double of the initial value. So the starting point won't change. Do you guys understand? You will start from the same value. However, what's going to happen is, since we have double the gradient, a certain value, the values afterwards will change. we now have a more negative gradient which is double the initial value. Okay, we have a more negative gradient which is double the initial value. So check this out. What did I pass through initially? Like, the intercept was 0, 2.9. And if you look at other values, okay, what can you figure out? They talked about a certain value in this graph. They use this value essentially. They use this value. We know that it was 1.8 at 0.9. So since the gradient is double now, what will happen? The change will be double. So rather than being 1.8, it's going to turn into 0.9 now at 4. It's going to turn into 0.9. So it's going to pass through this value over here, 0.9, and it will continue till 5. So let me explain again. Wait, give me a bit. It's so hard to control this. Yeah. Here you go. So you have to draw another graph, another straight line that has double the gradient as this. So the change will be double. It doesn't have to be this point, honestly. You can honestly use other points. For example, let me show you. For example, at 3.6, right? At 3.6, where were we? We were at 2. Okay. At 3.6, we were at 2. So rather than that, the change is actually going to be double over here. Let me show you why. Check this. For example, um, what's the change from 2.9 to 2? What's the change from 2.9 to 2? 2.9 minus 2 gives you a change of 0.9. So if you're at this point before, if there was a change of 0.9 before for a value of, time 3.6, the change is just going to be double now. So what's double of 0.9? It's 1.8. So what is 2.9 minus 1.8? It gives you a value of 1.1 instead. So rather than being at 2, you're going to be at 1.1 now, because the change has to be double, right? Because look at this change is actually 1.8. And now match the value. This will be the new value at 3.6 essentially. So check this. Here you go. So this will be the new value at 3.6. So, and look, our red line, my red line passes through that value as well. So they mentioned a particular value in the mark scheme, but if you used it with any other point, it would match. I'll tell you how the value in the mark scheme works out. Let me show you the logic. So we used this point at 4 seconds. It changed to 1.8. What's the change between 2.9 and 1.8? 2.9 minus 1.8 gives you a value of 1.1. So what's double the change of 1.1? It's 2.2. So the total change is 2.2. 2.9 minus 2.2 gives you a value of 0.7. Sorry, this isn't 1.8, right? My bad. It's supposed to be 1.9. My bad. This value is 1.9. I'm sorry. So 2.9 minus 1.9. This is why they use the value, to make things easier. Do you guys get it? The change is 1. But now rather than being 1, the change will be 2. So what is 2.9 minus 2? It is 0.9 essentially. So if you match the graph with 0.9, beforehand you were at, you know, you were at 1.9 at time 4 seconds, and the change was 1 from 2.9. But now the change will just be double of the initial value. It will be at 2 rather than 1 because the gradient has doubled. It is more negative now. So if you compare the change, it's 2 now. 2.9 minus 2 is 0.9. So your new point will be 0.9 on the y-axis at a time of 4 seconds. That's how it works out, okay? We get double the change. See if this makes sense. There was another route to find out the point. You could just take a random value, okay? You could just take a random value to find out your new point. For example, let me show you. You guys know the value of gradient, right? So check this. We know the time, right? What if I use a time of 4? I'm just going to use a time of 4. Check this. So ln q is equal to, the new gradient is now 2 times the previous one. So my previous one was minus 0.25. Now it's going to be minus 0.5. And the time is going to be 4 seconds. And ln q naught is going to be, how much was it? 2.9, right? So 2.9. So check this. If you just solve this equation, 0.5 into 4 minus answer plus 2.9 gives you an answer of 0.9. Ln q is equal to 0.9. That is how you get any point. So it doesn't have to be this point specifically. You can use any other point. You're going to get full marks for that, okay? So first time I'm seeing a linear equation for discharging a capacitor. Usually you get this sum, but this time they gave you this variation. Okay, moving on. We have 5 questions left now. A Hall probe is placed in a magnetic field. The Hall voltage is 0. The Hall probe is rotated to a new position in the magnetic field. It is now a maximum. Explain this observation. So we've moved to a position which is 90 degrees to the field. And initially we were parallel to the plate, right? So let's explain this. We can mention it this way. The reading is 0 when the plane of the probe was parallel to the magnetic field lines. When plane of the probe is parallel to the field lines, okay, to the magnetic field lines. Whoa, wait up. And what about the next one? So when do we get the maximum value? When it's perpendicular, right? So reading is maximum when the plane of the probe reading is maximum when plane of the probe is perpendicular to magnetic field lines. Okay, pretty simple. Good. State the meaning of n. N is the number density of charge carriers, okay, or the number of charge carriers per unit volume. I is equal to n VQ. You know it from AS. Explain why a Hall probe is made of silicon rather than copper. So silicon has a low value of n. It's a semiconductor. So if you decrease the value of n, you will get a higher value of VH, which will reduce percentage error. Smaller value of n, so greater Hall voltage. Understood? Good luck for your exams, by the way, guys. It's in May. Hopefully you guys do great. Next, part C. A Hall probe gives a maximum reading of 24 millivolts when placed in a uniform magnetic field of flux density 32 millisisla. The same Hall probe is then placed in a magnetic field of fixed direction and varying flux density. The Hall probe is in a fixed angle, so the angle between the Hall probe and the magnetic field is same as when the Hall voltage was 24 millivolts. The variation of the Hall voltage of the probe with time t from 0 to 8.6 is shown. Okay, so we have calibrated it with a known field. Okay, we have calibrated with the known field and now we're ready. So calculate the magnitude of the EMF induced in the coil between 0 and 8.6, maximum EMF. So you guys know something, right? You guys know that the formula for E is actually induced EMF according to Faraday's law is BAN by del T. Understood? So this sum is a bit tricky. In what sense? Hear me out. A Hall probe gives a maximum reading of 24 millivolt when placed in a uniform field of 32 millitesla. So we can use this information to find out the magnetic field strength over here, since it's calibrated beforehand. So since 24 millivolts corresponds to 32 millitesla, what will 36 millivolts correspond to? 32 divided by 24 times 36 millitesla. 32 by 24 times 32. This gives you a value of 48 millitesla. Okay, we need to mention this in the question that 36 millivolts actually corresponds to 48 millitesla. Okay, you need to mention this. And now let's do the math. Where do we get maximum EMF? Clearly it is the section on the right hand side because the gradient is maximum there, right? So I'm going to ignore the section on the left hand side and I'm going to work with this. So the time is 7.2 seconds and it ends at 8.6. 7.2 to 8.6. How much is that? 8.6 minus 7.2. So the time is 1.4 seconds. T is equal to 8.6 minus 7.2, which is 1.4 seconds. So E is actually equal to del B. What's the change in B? It went from 36 millivolt corresponds to 48 millitesla, right? So it went from 48 millitesla to 0. So 48 millitesla times what's the area of the coil? Diameter is 3.6. So radius is 1.8 centimeter. So pi into 1.8 into 10 to the power minus 2 whole square pi r square times n 780 turns divided by the time taken, which is 1.4. Let's do this. Oh, also, since it's 48 millitesla, we have to multiply 48 with 10 to the power minus 3 is equal to 48 into 10 to the power minus 3. Let's do this. So yeah, they've added a new variation. I haven't seen this before. 48 into 10 to the power minus 3 times pi times 1.8 into 10 to the power minus 2 whole square times 780 divided by 1.4. This gives you a value of 0.027 to 2SF. 0.027 volts to 2SF. Alright, great. Moving on to question number 7. We only have 4 questions left, 7, 8, 9, and 10. It won't take long. A beam of white light passes through a cloud of cool gas. The spectrum of the transmitted light is viewed and contains a number of dark lines. Explain why these dark lines occur. Perfect. So this is a repeat question. You've seen this question back in May, June 2020. This question was there. So what happens when a beam of light passes through cool gas? We get an absorption spectrum. Okay, so essentially the photons will interact with the electrons in the gas. And what happens? The photon is absorbed by electron in the gas and electron gets excited. And electron is excited or jumps up to a higher energy level. Now what? So this photon that the electron absorbed, the photon actually has energy equal to the gap between two levels, equal to the difference in energy of two energy levels. That's a weird way to word it. Photon energy equal to difference in energy of two energy levels. Okay, fine. Awesome. So this photon energy actually corresponds to a particular frequency. So this photon energy relates to a single wavelength or frequency. Relates to a single frequency or single wavelength. Okay, great. Now what? What's the fourth and final point? So why don't we get the photons in the spectrum though? Because the electrons don't stay excited forever. They will come back down, but in the process of doing so, they are emitted randomly in all directions. So we have to mention this, that the electron de-excites. The electron de-excites and emits photons in random directions. This is it. They wrote any though rather than random. They wrote any directions. Okay, that's fine. So this is the latest mark scheme. We are going to learn this. Some energy levels for the electron in an isolated hydrogen atom are shown. The energy associated with energy level N2 is minus 3.40. Table 7.1 shows the wavelengths of photons that are emitted in the transitions to n is equal to 2 from the other energy levels shown in figure 7.1. So we are transitioning to this level from these other levels. Okay, so we are going towards 2. There was a same question in October November 2022 variant 4.2. Calculate the energy in joules of energy level n is equal to 3. Okay, this is interesting. So let's draw all the transitions. Let's do this. So this is one transition. This is another one. This is the other one. And this is our final transition over here. So remember, the longer, since they said that we are transitioning to n is equal to 2 from the other levels. Okay, so now remember that the longer the line, the higher the energy, and energy is inversely proportional to wavelength. So this blue line actually corresponds to the smallest wavelength, 412 nanometer. And what about this light green line over here? It corresponds to the highest wavelength of 658 nanometers. Okay, so using that, I can actually find out the energy difference. Okay, so it's always going to be uh, the higher energy minus the lower energy. Let me show you what I mean. So we can write that F lambda or E is equal to hc by lambda. Hc by lambda is actually equal to the difference in energy between two levels, E1 minus E2. Now I'm actually going to use 656, right? 658, it should be 658 nanometers. They wrote 656 in the mark scheme for some reason. So 6.63 into 10 to the power minus 34 times 3.00 into 10 to the power 8 divided by 658 into 10 to the power minus 9 nanometers is actually equal to E1, okay, the higher one. We are calling this E1 and we are calling this E2. So E1 minus what is this? 3.40 electron volt. So 3.40, I'm converting electron volt to joules. How? By multiplying it 1.60 into 10 to the power minus 19. So let's do this step by step. 6.63 into 10 to the power minus 34 times 3 into 10 to the power 8 divided by 658 into 10 to the power minus 9. This gives you a value of 3.02 times 10 to the power minus 19 is equal to E1 plus, sorry, there was a minus sign here, minus minus gives you plus because it was inherently negative and this formula has a minus sign. So this turns into 3.4 into 10 to the power minus 19 times 1.6, which is 5.44 into 10 to the power minus 19. So now if you find it out, what's it going to be? 3.02 minus into 10 to the power minus 19 minus answer, which gives you E1 is actually equal to minus 2.4. How many significant figures do we have? We have 3SF, so I'm gonna opt for 3SF answer. 2.42 into 10 to the power minus 19 joules. Okay, perfect, guys. So yeah, this is the same sum that came in October November 2022 variant 4.1 or 4.2. I don't remember. You can check it out. It's pretty similar. Okay, last three questions. Let's finish this variant. I'm gonna wrap it up within 20 minutes, hopefully. So plutonium is unstable and undergoes alpha decay. So you know that an alpha particle is basically a helium nucleus. So this is going to be 4.2. So this is going to be 4 less 234. This is going to be 2 less 92. Okay, great. The power source in a space probe contains 0.874 kg of plutonium. Each nucleus of plutonium that decays emits 5.59 mega electron volts of energy. The half-life of plutonium is 87.7 years. Calculate the initial number of nuclei of plutonium-238 in the power source. Okay. So let's do this. We have the half-life, which we need later. Okay. The first step is actually pretty simple. You have the mass of plutonium. You also have the MR of plutonium, which is 238. Okay. So you can find out the mass of one atom of uranium. So what is the mass of one atom of uranium? It is essentially 238 times U, 1.66 into 10 to the power minus 27. This is the mass of one atom, and you have the total mass. So if you divide the total mass by one atom of plutonium, you are going to get, the total number of particles essentially, right? So we are getting a value of 2.21 into 10 to the power 24. There you go. Determine the initial activity. So you guys know that A is equal to lambda n. So we have n now, we have n naught, but we don't have lambda. But we can find out lambda because we know that T half is equal to ln 2 by lambda. So lambda is equal to ln 2 by T half, which is 87.7 years. Now we should definitely convert this to seconds. So that's 87.7 into 365 days into 24 hours into 3600 seconds. Crazy. So A is equal to ln 2 divided by 87.7 times 365 times 2400 times times 24 times 3600. This into n naught 2.21 into 10 to the power 24. Okay, let's do this. Ln 2 by 87.7 times 365 times 24 times 3600. So we get a value of A is equal to, correct to 3 significant figures because our data is given to 3SF, 5.54 times 10 to the power 14. And the unit is going to be becquerels because I converted to seconds. This is the SI unit. Use your answer in B2 to determine the initial power output from the source due to the decay of plutonium-238. Okay. So what is activity and what is lambda? Lambda is the probability of decay per unit time. And what is activity essentially? Is the actual number of particles that decay per second, right? So since it has per second attached to it, and since we know how much each plutonium gives out when it decays, we can just multiply this to get the answer. Okay. So simply put, the power will be the activity, because this gives us the number of plutonium nuclei decaying per second, times the energy emitted by each plutonium nucleus. So activity times 5.59. So let's do this. 5.54 times 10 to the power 14 times 5.59 times 10 to the power 6 times 1.60 into 10 to the power minus 19. I converted to joules. 5.59 into 10 to the power 6 times 1.6 into 10 to the power minus 19. Perfect. So we're getting an answer of 496, correct to 3SF. Nice. The space probe will continue to function until the power output from the plutonium in the source decreases to 65.3% of its initial value. Calculate the time in years for which the space probe will function. Okay. So essentially, we can just get rid of the power, because power essentially is activity. The 5.59 is just something extra because it's going to be cancelled out on each side. So we can just use the formula A is equal to A naught e to the power minus lambda t. And power, to get power, we just need to multiply n on each side, right? So that n is gonna change. It's not important over here. Sorry, we have to multiply. I meant, the energy from each decay. That is going to be common on each side, so it's not really essential. So I want the activity to become 0.653 of the 65.3%, or 0.653 times the initial activity. So what do we get? We can get rid of this on both sides. So basically we end up with this. We can say that ln 0.653 is equal to minus lambda t. So t is basically equal to minus ln 0.653. I'm not going to convert lambda to, I don't need to convert lambda to hours, seconds here, because they want the answer in, they want the answer in years here. So essentially, this is ln 0.653 is equal to minus ln 2 by t half, which is 87.7 times t. So what is t equals to? T is equal to ln 0.653 divided by, there's a minus here, ln 2 by 87.7. Let's do this. So minus ln 0.653 divided by ln 2 by 87.7. This gives us an answer of 53.9. T is equal to 53.9 years to 3SF, since the data is given to 3SF. An alternative power source uses energy generated from the radioactive decay of polonium-210. The isotope has a half-life of 0.378 years. The mass of the isotope needed for the same initial power output as in B is 3.37 grams. Okay. So yeah, we needed 0.874 kg there, which is crazy. 874 grams, but now we are just using 3.37 grams. So this is much more efficient, right? So the advantage is less mass needed, right? So less mass, so less energy needed. Less mass, so less energy needed to get probe into space. Okay, so that's great. But what's the disadvantage though? Look at the half-life, it's 0.378 years, but this one had a half-life of 87.7 years. So since it has a much shorter half-life, it will be used up very fast. So it won't be able to provide energy for a long time, okay? So that's the disadvantage. So the half-life is really short. So the half-life is shorter. So it will not provide power for long enough. So it will not provide power for long enough. Okay, that's the issue. All right, we're done with question number 7. Sorry, question number 8. Let's move on to 9 and 10, the last two. Explain how ultrasound waves are detected. Okay, so we basically use a piezoelectric crystal, right? So we refer to the piezoelectric crystal being used. Now, when the sound waves are reflected from the surface, body surface, or internal structures, it causes the crystal to vibrate. So the sound wave causes shape changes or vibrations essentially, and these shape changes or vibrations cause an EMF to be induced, which is detected. Okay, so the shape change or vibrations causes EMF, which is detected. That's great. So this is the latest mark scheme. We should follow this. And alternating voltage varies with time according to this equation. The root mean square value is 66. So for sinusoidal current, we know that VRMS or sinusoidal voltage, VRMS equals to V naught by root 2. So V naught is equal to root 2 times 66. Root 2 times 66 gives us a value of 93.3. We have 2 SF, so we're going to write 93 volts. Now what about omega? Omega is basically 2 pi by t or 2 pi f. So it's 2 pi times 4.3 times 10 to the power 6. That's huge. 2 pi times 4.3 times 10 to the power 6. That gives you a value of the 2SF 2.7 times 1, 2, 3, 4, 5, 6, 7. 10 power 7 rad per second. 2.7 times 10 to the power 7 rad per second. Table 9.1 contains information about air and soft tissue. Determine the unit for specific acoustic impedance. So we know that Z is equal to rho C. So rho is kilogram per meter cube and C is meter per second. So what do we end up with? Kg m minus 2 s minus 1. Kg m minus 2 s minus 1. Great. Calculate the density of soft tissue. Okay. So we know that Z is equal to rho C. So rho is equal to Z by C. So rho is equal to Z, which is 1.7 times 10 to the power 6 divided by C, 1600. This gives you a value of 1062.5. So we're going to round it off to 2SF since our data is given to 2SF. It's 1100. Use data from table 9.1 to explain why ultrasound can be used to produce an image inside an air-filled cavity such as the lungs. So ultrasound isn't used for air-filled cavities. Okay. It's mainly used for structures in the abdomen, the pelvis, etc. Mainly because air, alright, we got a value of 1100. Look at the difference of Z here. The difference in Z between Z is huge for air and soft tissue. So what's the issue? We know that alpha, the intensity reflection coefficient, is Z1 minus Z2 divided by Z1 plus Z2 whole square. So the larger the difference, the greater the value of alpha, and that means that more ultrasound will be reflected. So the ultrasound will not be able to penetrate the tissue. Most of it will be reflected, none of it will be transmitted. That is why we use a coupling medium, gel, on the skin, but we can't really apply gel on the lungs, can we, right? So that's why we can't use that, okay? So the coefficient is almost equal to 1 alpha. So you can calculate Z over here. Let's find out alpha. 4.3, sorry, why don't we use 1.7 times 10 to the power 6 minus 4.3 times 10 to the power 2 whole square divided by 1.7 times 10 to the power 6 plus 4.3 times 10 to the power 2 whole square. Let's do this. This was a pretty big paper though, honestly. So I'm getting a value of 0.999 actually. Okay, so you could show this and you could say that the calculation of intensity reflection coefficient is equal to 0.999 or essentially 1.0. So what does that mean? Since the coefficient is approximately equal to 1, this means that almost all or essentially all ultrasound, not almost, all ultrasound is reflected. This is the meaning. Okay. So the closer they are, the closer that the coefficient is to 0 and the more ultrasound is transmitted. Okay. Moving on to the last question for the day. Question number 10. A student observes different stars from the Earth. Give 2 reasons why some stars appear brighter than others. So one of the reasons could be luminosity. The greater the luminosity, the greater the brightness, and the other might be distance. One star might be closer. Okay. So the brighter star could be closer, or you could basically say that the brighter star could have greater luminosity in the visible wavelengths. A brighter star is hotter is also allowed. Okay. the brighter star could have a greater luminosity. The brightest star could have a greater luminosity in the visible wavelengths. They allowed brighter star is hotter, or just the brighter star has greater luminosity. Okay, nice. What is meant by standard candle? Okay, so it's honestly a star or galaxy with known luminosity. So it is an object with known luminosity. That's it. Fine. A spectral line from a star with a galaxy is observed to have a wavelength of 660.9 nanometer. The same spectral line measured in the laboratory is observed to have a wavelength of 656.3 nanometers. So honestly, guys, this is the OG, the original wavelength, and this is the increased wavelength due to Doppler redshift. You know that the universe is expanding and stars are moving away from each other. Show that the relative speed, the speed of the star relative to the Earth, is 2.1 into 10 power 6. So we're going to use the formula for Doppler redshift, which is this. Check this. It was added to the syllabus in 2020. This one. So del lambda by lambda is equal to V by C. Del lambda by lambda equals to V by C. Okay. So del lambda by lambda is equal to V by C, where del lambda is the difference in wavelength and lambda is the original wavelength, original, not the new one, the lower one. Okay. So let's do this. What is del lambda? 660.9 minus 656.3 divided by the original one, the lower one, 656.3 nanometer, is equal to the speed of recession divided by the speed of light. So let's do this. 660.9 minus 656.3 divided by 656.3 times 3 into 10 to the power 8. By the way, don't use the equal to sign. Please use approximately equal to. That's what they wrote in the mark scheme. So V is equal to, approximately equal to 2.1 times 10 to the power 6 meter per second. Okay. Now calculate the distance of the star given that the Hubble constant is 2.3 into 10 power minus 18. So we know that the speed of recession is actually is proportional to the distance between the two stars. So V is actually equal to Hubble constant times the distance. So if you want to find out the distance, it's going to be the speed 2.1 into 10 power 6 divided by the Hubble constant 2.3 into 10 to the power minus 18. I'm using my calculator value 2.3 into 10 power minus 18. This gives me a value of d is equal to 9.1 into 10 to the power 23 to 2SF, since our data is given to 2SF. State and explain what can be concluded about the universe based on this change in the observed wavelength. That's perfect. So basically, the light has redshifted, or the wavelength has increased. So basically what has happened, our observation is that the wavelength has increased, or basically light is redshifted. That is our observation. And let's explain this change. What consequence does this have? This means that galaxies, or in general, the galaxy is moving away from Earth. And not just Earth, galaxies are moving away from each other, and ultimately the universe is expanding. These are the three marking points. Okay, so guys, that is it for today. Overall, I'd say that the second part of the question paper was pretty easy. It was pretty average. We had some common questions. There were a few things that were a bit uncommon, like, this question was new. You had to see this for the first time. Then yeah, this question was a bit hard if you aren't good at mechanics. And yeah, everything else was fine. It was alright. It was average in difficulty. Some parts were a bit hard, maybe 30 to 40 marks. But I need to confirm about question number 1 though, because the mark scheme might be wrong since it's pre-standardized. I'll let you guys know in the comment section if I do find anything out. Till then, good luck for your exams. Hopefully this helped you. I'm gonna link the paper for February March 2022 paper 4.2 up here, and the paper for May June 2022 paper 4.2 down here, and the playlist for physics paper 4 up here, and subscribe to the channel if you like the content. See you guys.